In section 7.5, we're going to finish our chapter by working on writing recursive rules. Recursive rules are different from explicit rules in that an explicit rule, something like this, a sub n is equal to 2n minus 1, this allows me to find any term based on knowing its place within the sequence. So the value of n is a term's place in the sequence. When we start talking about a recursive rule, recursive means you're looking backwards. So we're talking about relating a term to the term before it. So instead of writing a rule that allows us to find it based on knowing its place in the sequence, we'll be able to find a term based on knowing the term before it. Okay, so this is what an explicit rule is. This is your vocabulary. This is what a recursive rule is. And when we talk about iteration, we're talking about making iterative changes means making the same change repetitively in a number pattern. So that's what happens when you build a sequence based on a recursive rule. So the type of problem we might use to solve this is looking at doing an analysis here of an online music service. And they initially had 50,000 annual members, but each year they lose 20% of their current members, but add 5,000 new members. So if you want to now track their membership, we would want to write a recursive rule for the number of members, and then find the members at the start of the 5th year and describe what happens to our number of members over time. So what we'll do is we'll write our recursive rule, and then we'll go through the iterative process to build out the sequence to the 5th year and see what happens. Okay, but before we do that, let's work a little bit with recursive rules. So again, this is a repeat of what I had already said. An explicit rule gives you your term as a function of its position in the sequence. A recursive rule gives the beginning term, and then it allows you to find the next term based on knowing the term before it. So if I wanted to find a number of terms, they've told me the first term, and they give me a recursive rule. So a term is equal to the term before it plus 3. So I know that a sub 1 is 1. If I want to do a sub 2, it's equal to a sub 1 plus 3, which would be 4. A sub 3 would be equal to a sub 2 plus 3. A sub 2 was 4. 4 plus 3 is 7. So you can see that really what we're doing is we're going through and we're just adding 3 each time. But until I know the term before, I can't add 3 to it. So that's what sort of works out with the recursive rule. This one's a little more complicated. So it says that a term is equal to the term before it times the term 2 before it. So I know in this case they have to give me 2 terms. They have to give me 1 and 2 so that I can find a sub 3 would be equal to a sub 2 times a sub 1. That would be 2 times 3, which would be 6. Now a sub 4 will be equal to a sub 3 times a sub 2. Well, a sub 3 was 6, a sub 2 was 3, so that'll be 18. A sub 5 would be equal to a sub 4, which was 18, times a sub 3, which would be 6. So that'd be 60 and 48, that's 108. Okay, and that's how recursive rules work. So you can build the sequence, but you have to build it one term at a time. So go ahead and practice that. Do problems 6, 7, and 8. And then come on back and we'll look at something else. So we have rules for building recursive equations. If it has an arithmetic sequence and I know the common difference, my recursive rule will always be a sub n is equal to a sub n minus 1. And remember, a sub n is just a term, an unknown term. A sub n minus 1 is the term before it. Okay, so a term is equal to the term before it plus the common difference. And if we're looking at geometric sequences, a term is equal to the term before it times the common ratio. Okay, so it's really rather simple, but if you want to write a recursive rule, first you'd have to know which type of sequence you had, and you'd have to find the common difference or the common ratio. So if I take a look at this sequence. 14 minus 21 is 7. Sorry, negative 7. 7 minus 14 is negative 7. 0 minus 7 is negative 7. So my common difference, I found it by subtracting, is negative 7. So my recursive rule will be a sub n is equal to a sub n minus 1. They all start this way. Plus my common difference, which would be negative 7. And if I simplified that, a term is equal to the term before it minus 7. That's my recursive rule. And you can see if you follow this, 21 minus 7 gives me 14. 14 minus 7 gives me 7. 7 minus 7 gives me 0. 0 minus 7 gives me negative 7. It works for my rule. Okay, if we look at this one, 12 minus 3 is 9. 48 minus 12 is 36. So this is not arithmetic. But 12 divided by 3 is 4. 48 divided by 12 is 4. So 192 divided by 48 is 4. So I know my common ratio is 4. So my recursive rule, a term is equal to the term before it times my common ratio, 4. Okay, so that's how you write recursive rules. So now in this particular case, so this one's a little different. So I have to sort of figure out what's going on with this. 5 minus 3 is 2. 15 minus 5 is 10. So it's not arithmetic. 5 divided by 3 is 5/3. 15 divided by 5 is 3. Okay, so it's not geometric either. So this is a special sequence. That's what's making this special. So what I want to try to do is look at my number pattern and what's going on. And what's interesting and what I notice really quick is I notice that 15 is 3 times 5. 75 is 5 times 15. Okay, so what I'm getting is that a term is equal to the two terms before it multiplied together. So a sub n would be equal to the term before it, a sub n minus 1, times the term before that, a sub n minus 2. Okay, so again, when you're working with number patterns, you're just trying to figure out what's going on. It's nice when they fit the arithmetic or the geometric mold, but they don't always. So when it's not arithmetic and it's not geometric and you still want to write the recursive rule, you have to kind of look at it and figure out what the heck is going on with this, and then write a rule that represents that relation. So go ahead and give some practice to that. Do 16, 17, 18, and 21, and then come on back. And we'll talk about iterating a function. So iterating a function involves the repeated composition of a function f within itself, which in essence is what we do. If I'm building a full sequence based off building one term and then the next term and the next term and the next term, that's what I'm doing. I'm really doing the composite of a function as I find each term. So if I wanted to find specific terms, right, you can see that what all they're really saying is that as you're going through with a recursive rule, all you're doing is plugging outputs back into the function over and over and over again. So if I want to find x sub 1, that's going to be equal to the function of x sub 0. So I'll have 5 times negative 2 plus 6. So this would be equal to 5 times negative 2 is negative 10. Negative 10 plus 6 is negative 4. Then if I want to find x sub 2, see, we're doing the same thing we were doing before with the recursive rule. It's 5 times negative 4 plus 6. Negative 20 plus 6 is negative 14. X sub 3 would be 5 times negative 14 plus 6. So negative 70 plus 6 is equal to negative 64. Right? And when we go through, we can go as far as we want. We just keep taking, you notice I take the result here. I take the result here and I plug it into the equation in the next line. I take the result of that and I plug it into the equation in the next line, and I can do this forever. Okay, so let's do one more example and then we'll solve our word problem. So I know that x sub 1 would be equal to, 3 times 2 minus 2. 6 minus 2 is 4. X sub 2 would be equal to 3 times 4 minus 2. 12 minus 2 is 10. X sub 3 would be equal to 3 times 10 minus 2. 30 minus 2 is 28, and so on. We can go on that way. So this is about being iterative with the function. And if I wanted specifically to find, the fifth, if I didn't want to find all the terms, I could repetitively composite this function to make a single function that would find x sub 5. I'm not sure it would be any easier than what I'm doing right now. But go ahead and practice this. Do problems 27 and 28. Come on back and we'll wrap up this last lesson from chapter 7. So when you look at what's happening with this function, we know that any term we have will be equal to the term before it, losing 20%. So that means it would be 80% of itself times 0.8 plus 5,000 new members. All right, so that's the way this rule will work. So what I took is, I know that a sub 1 is equal to 50,000. That's what we have. A sub 1 is equal to 50,000. That's where we start. That's where we are in the very first year. Right? So now, if I want to go ahead and find out what happens at the start of the 5th year, let's go ahead and let's go through. We know that a sub 2 will be equal to 50,000 times 0.8 plus 5,000. So 50,000 times 0.8, that's 40,000, plus 5,000 is 45,000. Right, now if I want to do a sub 3, that's going to be 45,000 times 0.8 plus 5,000. So in this case, it's going to be 36,000 plus 5,000. That becomes 41,000. A sub 4 is going to be my 41,000 times 0.8 plus 5,000. Now I'm going to have to pull out a calculator. So let me get my calculator. So I'll have 41,000 times 0.8 is 32. Oops, I wrote too big a number, didn't I? So 41,000 times 0.8 is 32.8 plus 5,000, 37.8. All right, and if we go ahead and do the 5th year, 37.8 times 0.8 plus 5,000. We'll go back to the calculator. Times 0.8 equals plus 5,000 equals 35,240. So if you see what's going on here, here I lost 4,000. If I go from here to here, I lost 3,200. As I go from here to here, I lost, less than 2,600, 2,500 and so on. So the amount of members that I lose each year is decreasing. And what you can see is when I reach the point that the number of members I have, where 20% of the number of members I have will be 5,000, then I'll lose 5,000 and I'll gain 5,000 and we'll eventually hit a plateau. Okay, so what I need to know is that, right, when you look at 80%, whenever I get down to the point where I have 25,000 members, 25,000 times 0.8 plus 5,000, whenever I get there, it looks like it's going to be a little while. But when I get to 25,000 times 0.8, that's going to be 20,000 plus 5,000. That'll be 25. So my membership will remain static at that point at 25,000. Right? So that's how you would use this kind of concept within the constraints. Remember, to solve the problem, what I did is I built up what happened over the first 5 years, and then I examined it. And what does it mean? The amount of membership we were losing was decreasing over time, and where it's eventually going to get to is what reaches 0, and then will remain static at 25. But it's very clear that when the 20% loss equals the 5,000 gain, our membership will remain consistent. Anyway, that's the end of chapter 7.